So yeah, let's start our day 6. So in today's session, we will discuss the ports in Verilog. So what are these ports and how we use these ports and what are the connections and what is the test bench environment. We will discuss about that. Before starting with the ports, so uh, I will discuss the plan, like how designers will design and how designers will test their design. So basically, there will be a design under test. It is called DUT, design under test. So this will be a block which is known as design under test. This is our design. Say, for example, our full adder or half adder or whatever we are coding. So this is our design underscore design under test. Wait a minute. Yeah, recording is on. So this is our design. So for testing this design, we will create an test bench environment. So here we will create a test bench. So what we will basically do is, for our design we will generate a stimulus with the help of this test bench. So from this test bench the signals will be driving to our design. So we will drive input signals to our design and we will get the corresponding output from our design, and we will verify the output whether we are getting the correct output or the expected output or not. For example, in the case of our full adder, the inputs for our design are inputs A, B and carry in. We will be supplying these inputs from our test bench. So we are supplying this inputs A, B and C in from our test bench, and we are getting output from our full adder, that is design under test, from the outputs sum and wait a minute. So we are getting our outputs called sum and carry out from our design, and we are capturing it in our test bench. So from our test bench we are driving inputs to our design, that is A, B, C, and we are getting outputs from our design and we are capturing them in our TB with the help of sum and carry out. So like this we will design a code and we will check whether our design is working properly or not with the help of a test bench. So for this, now let's discuss about ports, and we will come back to this topic later. So ports provide the interface by which a module can communicate with its environment. So here our discuss our discussed DUT will consist of ports. So with the help of these ports, our design will communicate with the external environment, that is our TB. In this case, our TB. So the design under test, that is our design, will communicate with our TB with the help of ports. So there are basically three types of ports. First type is input port. Second is output port, and third one is in output. So these ports are helping our design to communicate with the external environment, in this case our TV. So for example, here input and output pins of an IC chip are its ports, and the environment can interact with the module only through its port. Here in our case, the TB can interact with the design only with the help of ports, that is input port, output port and in output. Without these ports, this TB cannot interact with our design. So a module definition contains an optional list of ports, and if the module does not exchange any signals with the environment, there are no ports in the list. So let's take an example here. Let's take the full adder example only. Module full adder. The input ports for our module are, say example, input A, input B, input C. So these three are the input ports of our full adder, and coming to output, we have output sum and output carry. So these are the inputs and outputs of our full adder. So what happens is there will be our design. So in synthesis our design will be created, and for this input are A, B and C, and the outputs are sum and carry. And if we write a test bench for this design, then our TB will communicate with this input and output ports. The TB, here we will design such that our TB will generate stimulus, that is it will generate inputs A, B and C, and the design will take these inputs and it will produce sum and carry, and this sum and carry will be given back to our TB, and we will verify whether the uh, sum and carry are getting correctly according to the inputs given or not. So like this, with the help of the input ports, the design is communicating with the external environment. So if we do not declare any ports, there is we can also declare module without writing any ports. We can also declare any module without any ports. Generally, we will develop the test bench without declaring any ports. We will see about this in later. So a model can have a ports or it may not have any ports. It's up to the designer. So this is the usage of ports. So consider a 4-bit full adder that is instantiated inside a top level model. So we will take another example. Yeah, here it is. Wait a minute. So yeah, here there is a top level module present. This is a top level module, and in this top level module we have a full adder. This is our design. So full adder. This is a 4-bit full adder. This is our design. This top is nothing but this is we will take here. It has a TB. So for this TB, there are no input ports or output ports. So while developing the module for a TB, we can develop the module without any ports. Here in this diagram, we can see for our top or for our TB, there are no inputs or outputs. So we can write the module without writing any ports. And for our full adder, this is our design. We have 3 input ports A, B and C underscore in, and 2 outputs sum and C underscore out. A, B, C underscore in are our inputs. So while developing the module for our full adder, we will take input ports as A, B, C underscore in and output ports as sum and C underscore out. Like this, we will design the module and declare the input and output ports. Is this clear for everyone? Can we move forward? Are there any doubts? So for declaring input ports, we will use the keyword input, then it will be our input port. And for declaring our output ports, we will use the keyword output, then it will act as an output port. And for declaring in-out ports, we will, that is bidirectional, both input and output, we will use the keyword in-out. So the port will act both as an input and output at a time. So like this, we will declare the input, output and in-out ports. So each port in the port list is defined as input, output or in-out based on the direction of the port signal. So generally in the design specification, the user will be given what port is the output port or what port is the input port he will be giving. Then accordingly we will develop the model and we will declare the input and output ports, or according to the design we will declare the port as an input or output. Note that all the port declarations are implicitly declared as wire in Verilog. So here we declare a module, say DUT, and here there are some input ports, say input A, input B, and output C. Sorry, here also there should be a semicolon. Mistake. Here it is not comma, it's a semicolon. So let us consider a DUT module where we have input A, input B and output C. So here we are not declaring any reg or wire. So by default, all the ports will be of type wire. So this is a very important point to be remembered. If we are not declaring any port as reg or wire, then by default all the ports will be of type wire. This is a very important point. So if we want to declare any port as reg, then we can declare, or else no need to declare them as wire because they are by default of type wire. Generally we will declare output of type reg so that our output gets stored in this variable, or else if we don't want our output to get stored, then we will not declare them as reg, then they will be of type wire only. So by default all the ports are of type wire. And note that all the ports declarations are implicitly declared as wire in the Verilog, and thus if a port is intended to be a wire, it is sufficient to declare it as an output, input or in-out. If we want any particular port to be of reg type, or if we want to store any value, so we will declare the port as a reg, then it will store the value. And input or in-out ports are normally declared as wires. However, if output ports hold their values, then they must be declared as reg. So ports of the type input and in-out cannot be declared as reg because reg variables store values, and input ports should not store values but simply reflect the changes in the external signal they are connected to. So if there is a design here, generally when we are designing some design, there will be some inputs. These are my inputs and this is my output side. So when we are designing any design, what we what we mainly want is our output. If we want to analyze the output, then we want the values to be stored in the output. If we want to analyze the output, then definitely we want the values to be stored in the output. But in the input side, we will not want to analyze we will not want to analyze any values because we are only driving the inputs, so we will not analyze the outputs at input. So the inputs are mainly of wire type only. In Verilog the inputs are wire type only. We will not store any value in the input ports, but in the output we will store the value for analyzing purpose. So in the output side we will store the values for analyzing. So that's why we are using reg if needed at the output ports, but we will not declare reg at the input ports. We want the inputs to be driven continuously to the design, and we want the output that should be stored, and if we want we can analyze. So that's why here the inputs are of type wire mostly. So the ports of the type input and in-out cannot be declared as reg because reg variables store the values, and input ports should not store values but simply reflect the changes in the external signals they are connected to. So is this clear for everyone? Is there any doubt in this?
Yes, clear.
Okay, thank you. So this is also a very important topic, port connection rules. So wait a minute. Yeah, port connection rules. So let's say this is our design. In our design, say we have an input port. This is an internal signal. So in our design, this is our design, and we have an external environment. Say this is a TV. So for our design, we have one input port and one output port and one in-out port. So here input ports are of type wire or net. Here we can see internally input ports are of type wire only. So we cannot declare inputs as reg type. We can only declare inputs as net, and output can be reg or net. And in-out ports are should be of type net only. So when we are designing a module, we should take care that inputs are of type net and outputs are of type reg or net, and in-out should be of net type only. But when we are driving any signal to our design using the test bench, then here we can drive reg or net to our input. We can drive reg or net to our input, and while collecting the output, we can use only net type. This is our external signal. I am talking about externals. So while collecting the signals, the output should be of only net, and while giving the stimulus to our in-out port, the external signal should be net type only. We will see this with the help of the coding so that it will be a better clarity. It will give a better clarity. So our design internal should be, input should be of net type only. We should not use reg. And for our output port, it should be of reg or net, and for our in-out, it should be net. Whereas when driving externally with the help of TB, the for input ports we should drive reg or net values. We can drive both reg or net, and when capturing an output, we should store it in a net. Whereas for in-out also it should be a net data type. So this is the port connection rules which we should follow. So internally input ports must always be of type net. Externally the inputs can be connected to a variable which is a reg or a net. This is about input ports. And coming to output ports, internally output ports can be of the type reg or net. Externally outputs must always be connected to a net. They cannot be connected to a reg. So this is the point to be remembered. Internally outputs can be of type reg or net, but externally outputs must always be connected to a net. Outputs must always be connected to a net externally. They cannot be connected to a reg. And internally in-out ports must always be of type net, but externally in-out ports must always be connected to a net. Here we can see internally in-out ports are declared as nets, and externally also we should connect them to a net. And it is illegal to connect internal and external items of different sizes when making inter-module port connections. So if we have a design and we are driving the stimulus with the help of a test bench, and we have an input port of 4 bits size, and if we are connecting this input port with an external port which is coming from our test bench, this external port is of 8-bit. So the width can be different, but it is illegal to be different. Here it is mentioned that it is illegal to connect internal and external items of different sizes when making inter-module port connections. However, a warning is typically issued that the width does not match. So the ports with different widths should not be connected. It will generate a warning. So this is about the port connections and port connection rules, inputs, outputs, and in-out port connections. So is this clear for everyone? Is there any particular doubt here? So please install some simulator so that we can parallelly practice. So let me create a design source. You can also install model sim if you want, or else you can also install Vivado. So I've created a project and I'm creating a design source, add sources. I'm taking the example of a full adder. Next, full underscore adder. Okay, finish it. Let me maximize it. Let me zoom it. Is it visible, right?
Yes.
So like this, I have created a full adder module, and for this, I have input ports A, B, C, and outputs. I'm taking inputs as 1 bit only, and outputs also 1 bit. Output sum and carry. Sum is nothing but since wait a minute, I will declare it as a reg. Um, equation of sum is so within an always begin block we should assign the values. We will discuss about this always begin block and initial begin block in our upcoming sessions. So for now, within an always begin block, we will assign sum is equal to A XOR B XOR C, and carry is equal to A and B, or with C in or A, sorry, C and A, or with A and B and C. So this is the equation of sum and carry, and we will end this always at the rate star. I will explain this what is star and everything, but for now I'm trying to explain this port concept. So like this, I have declared a module with input ports and output ports, and I'm assigning output which is equal to AX or BX or C, and carry is equal to A and B, or with C and A, or with B and C. So this is our design. So for our design, for testing our design, we will create a test bench. So I'm going to simulation sources, right click, add sources, create file. So here dut underscore tb, I will give some name, okay, and finish it, okay, yes. Wait a minute, it's getting updated. Yeah. So for our dut underscore tb, I will not give any ports since it is our external environment. I have explained it. Wait a minute, I will draw a diagram so that it will be more clear. Yeah, here we can see. So this is our full adder. So this is our full adder module. So I have created some input ports and output ports. And for this full adder module, now I'm writing a test bench environment. So this test bench environment will provide inputs and will take outputs from this environment. So this test bench will not have any ports, input or output ports. So design accordingly. I will declare some registers as A, B, C, and for outputs, the external should be and the outputs of the design should be connected to wire type. So it should be wire sum and carry out. And now I want to connect this design to now I want to connect this test bench to our design. So this is our test bench. Now I want to connect this test bench to our design, that is full adder. So this connection is done by instantiation. So this is there is a concept called instantiation. So with the help of instantiation we will connect our test bench to our design. We will discuss about this instantiation. There will be two types of instantiation. One is port instantiation and one is name based instantiation. So I will use, sorry, one is a position based instantiation and another is name based instantiation. I will use position based for now. We will discuss about that instantiation later. So for connecting this test bench to our design, we will write this full underscore adder here. Full underscore adder. We should write the design name followed by some optional name. So full underscore adder is our design name followed by some optional name for our design name. So I am taking DUT. This can be anything. And in a positional based instantiation I'm using, I will explain this in upcoming videos. So I'm now using positional based instantiation, some comma carry underscore out. Yeah, and within an initial beginning block I'm driving this a is equal to 0, b is equal to 0, and c in is equal to 0. I'm forgetting this semicolon here. Yeah. Ending this and ending the module. Yeah. So I've just simply driven all zeros. So here I have connected my DUT to test bench. So this concept is called instantiation. I'll write it here. So with the help of positional based instantiation, I'm connecting my test bench to DUT and I'm driving stimulus from my test bench to DUT. So here we can see the hierarchy being updated. Here we can see. So in our DUT underscore TB, there is a full adder. So this test bench is being connected to our full adder. So by this instantiation, this test bench get connected to our full adder. Now let me run simulation. Wait a minute. We should make sure that in the design source, our design should be top. So our full adder should be top. So right click on it and set as top. So yeah, now our full adder model is top. So we'll now run the simulation. So if you don't know about this Vivada tool, we will discuss about this tool also on some like Saturday or Sunday. If you want, you can message in the group. Then we can discuss about this Vivada tool. Yeah, here we can see at the simulation I'm just driving a is equal to 0, b is equal to 0, and c in is equal to 0 only. So I'm getting sum is equal to 0 and carry is equal to 0 in this now I'm more interested in showing how this DUT is connecting to our full ladder, and how these ports are being declared, and for these ports how I am writing, how I am making connections. So for inputs I am taking reg, and for outputs we should take wire only. So what happens if we take reg for our outputs? Let's see here. So I'm taking reg sum comma carry comma, sorry, sum comma carry underscore out, and let's check our simulation and simulation. Yes, I want to rerun it again. So let's see what happens if we take outputs as reg. What happens if we connect our design outputs to reg? So we are getting an error. See, concurrent assignment to a non-net sum is not permitted. So like this, we will get an error if we try to connect our outputs to a reg type. So we should connect our outputs to a wire or net type. So like this, we should be careful while connecting the port connections. So this is what I wanted to explain in this session. So this is all about